Hey, welcome. This is going to serve for our lesson for 10.2.2 if you're absent or if you just wanted to review. Just the way that we solve a perfect square equation, and then it goes into how we solve an absolute value equation. We're going to start off with a perfect square equation. This is a perfect square equation because we have what we see in front of us as a perfect square group. That's this piece right here. All right, that piece right there that says a group being squared, that's going to be a perfect square trinomial, and that's why this is a perfect square equation. All right, so to solve this, you could start by rewriting it, which would mean to use FOIL or a generic rectangle to multiply these two binomials, x minus 3 times itself, and you could get that all worked out, factor it, but it's a big pain in the butt. There's an easier route to go. The easier route to go is to undo what's being done here. Well, what's being done is I've got a value x, and if I knew that value x, I would first subtract 3, and then I would square it. I would use the exponent to square it. So if we're going to undo, I'm going to go backwards through that. I'm going to undo the square first by doing the opposite, which is to square root that left side. What I do to one side, I must also do to the other. These will cancel out, leaving me with x minus 3. On the other side, however, I get the square root of 12. All right? If I were to go down to a decimal, that's an irrational decimal. All right? But I have to think to myself, it's not just the square root of 12, all right? Not the positive result. I was really asking what squared is 12. Well, we have to remember that the positive result of that will work, but there's also a negative result that will also work. So really, I have to take my x minus 3 and set it equal to both a positive and negative 12. From here, I can continue to solve by adding 3 to both sides, giving me x equals 3 plus or minus the square root of 12. That would be the very exact answer if you wanted a very exact one. But if you wanted to go ahead and get yourself a decimal approximate, you could just do 3 plus the square root of 12. All right, and you could round that to 2 decimal places, saying that x is approximately 6.46. Or you could take 3 minus the square root of 12, and you could round that to 2 decimal places, getting approximately negative 0.46. And those would be our two approximate answers that would make this equation true. Okay? If you knew if the square root of 12 was actually a rational number, you would get nice whole numbers here. Let's take a look now at absolute value. In the same way that perfect square groups got us 2 answers when it was set equal to a positive number, we see that absolute value also gets us 2 answers when it's set equal to a positive number. Because what I have to do here is I have to first cover up what's inside my absolute value and ask myself, what has an absolute value that's equal to 9? Well, if we answer that question, we would find that both 9 or negative 9 would work to make that true. So what I'm covering must equal 9 or negative 9. Well, what I was covering is 2x minus 5. That means that 2x minus 5 must equal 9 or 2x minus 5 must equal negative 9. And that gives me 2 equations that I can solve to find the 2 values of x that would make this true. We would solve both of these using the same steps because it's just 2x minus 5, and I'm looking to do the opposite here. All right, we'd find that x in this case could be either 7 or negative 2. Both values will make that true, just like a perfect square group. For the sake of comparison, I'd like to take a moment to solve the perfect square of 2x minus 5 equals to 9. So let's go ahead and solve this just like we did earlier when we saw the first problem today. Let's square root both sides. All right, when I square root both sides, that's going to undo this right here, leaving me with 2x minus 5 is equal to the square root of 9 is both positive 3 and negative 3. I'm going to split this off into 2 equations here, unlike I did in the first problem, because I noticed that to solve 2x minus 5, it's actually going to be 2 steps. And so it's going to be a little bit more challenging to use that 2x, the plus and minus 3 symbol as we saw there. All right, so I'm going to do 1 equal to positive 3, 1 equal to negative 3. And I'm going to solve this using the same steps that we used before, adding 5 to both sides and dividing by 2. All right, that gives me 8 divided by 2 is 4. So x could equal 4, or 1. X could equal 4 or 1. So now we see the summary of our two things that we're looking at here. We're looking at perfect square groups and absolute value groups. Both of these situations gave us two answers. All right, because when we found out what squared is 9, there were two results. Both 3 and negative 3 could be squared to get 9. When we looked at what had an absolute value of 9, there were two results. Both 9 and negative 9 have an absolute value of 9, giving us two tracks to get two answers. Why? Let's take a look at the graph for a moment to see why this is true. On our graph here, we see that we've got the parabola of 2x minus 5 squared. It's a perfect square trinomial here. And we can see we've got another line. Our green line represents the value of 9. The question that we're essentially asking when I give you this right here, this equation, what we're essentially asking is, when will the parabola of 2x minus 5 squared equal 9? Well, we can see here there are two spots where it will equal 9. When x is 1, all right, and when x is 4, we will have a value of 9. And that's what we see. There's two spots. The line crosses twice. That's why there's two answers. Let's take a moment to look at our absolute value graph. All right, here's our absolute value graph when we look at 9. And as we compare this, we can see there are, again, two spots where our absolute value graph comes back around to equal 9, both when x is negative 2 and when x is 7. This is exactly what we identify when we solve these. We can see that x was 4 and 1 to make our perfect square group 9, and x was 7 and negative 2 to make our absolute value graph 9. Let's explore this a little bit further because that's when they equal a positive. But let's take a look here to see what about if I change the value that they're equal to, if I change that y value and I start moving it down. Notice here, it's still positive. I'm at positive 2 right now, and it still crosses each of those graphs twice. There's my absolute value graph. It crosses at 1.5 and 3.5. And there's my parabola where it crosses at approximately 1.79 and approximately 2.1. All right. So as we look at that, it still crosses twice. But what if I get down to 0? How many times does it cross now? Well, for both of these, it crosses once when x is 2.5. There's only one time where both of those will equal 0. That's because when we look at this process, if I were to go to solve either of these, if I used my cover-up method and I asked what squared is 0, you would only be able to tell me one result, 0. Likewise, if I used the cover-up method over here and I said what has an absolute value of 0, you would only be able to tell me one result. That result is 0. So as I go to solve these, if I were to do the square root over here, I'd find that 2x minus 5 equals 0. Not positive 0, not negative 0. 0 is neither of those. It's just 0. And if I were to solve that by adding 5 on both sides, I would find out that in order to get the value of x that makes this true, I would find that x would have to be 2.5. That's what would make it true. Likewise over here, 2x minus 5, this will only be true when 2x minus 5 is 0. And if I solve that, I get the same result of 2.5. That's what we see on our graph here. The value where these graphs hit 0 is when x is 2.5, and there's only one time they touch, and that's at the vertex for both. What if I go further? What if I take a perfect square group or an absolute value group and set it equal to a negative? All right, now take a look. Where do my parabola or v-graph cross that green line? Well, they don't. They don't touch it at all. They don't cross the x-axis. They don't go into the negatives. All right? So when we look at this next step, we see now if either our perfect square group or our absolute value group are set equal to a negative, we end up at this point with no solution. There's no value of x that will ever make those graphs hit a negative. All right? Because there's nothing squared that you could plug in to equal negative. Anything squared is positive. There's nothing that you could plug into an absolute value group that would turn it to a negative number. Absolute value always makes things positive. What these two have in common, squaring something and taking the absolute value of something, is that the result will always be a positive number. And that's why our graphs bounce back. All right? They don't just stay. They don't go down into the negative. They don't continue down this direction. They hit that x-axis and they bounce back up. They're going down, 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 and then they hit that x-axis and they bounce back up again. They do not enter into the negative because neither of them can ever have a negative result. So let's just recap a little bit. If our square group and our absolute value group are equal to a positive number, then there will be two solutions. Sometimes those solutions are irrational, as we saw in the beginning when we couldn't take the square root of 12 and get a nice rational number. Sometimes they're nice whole numbers if the perfect square number on the other side will get us a rational result. With absolute value, it's typically a rational number, whether it's a whole number or fraction will vary, all right? But if it's equal to a positive number, you'll get two answers. If our perfect square group or our absolute value group is set equal to 0, then you will get one solution and one solution only. And if our perfect square group or our absolute value group are set equal to a negative number, you will end up with no solution. Let me just give you two final examples based on that conclusion, because I don't want you to look at these problems and automatically assume how many solutions there are. Take a look at the left. It is set equal to 0. All right, the original equation is set equal to 0, but that does not mean in this case that there's only one solution, because it's not our squared group that's set equal to 0. In order to solve a perfect square equation, we must first get it alone. So I've got to move that 3 to the other side. At this point, now I see that it's going to be equal to a positive number, which is going to get me two solutions. And you can continue to solve that out, going to take a square root both sides and going from there. All right. On this other side, notice it is a negative 4 in front of our absolute value, and you might think this is going to generate no solutions because it's equal to a negative. But again, we got to get that absolute value group alone first. I'm going to divide by negative 4. That is the opposite of multiplication, so it will undo it. If I do that, I find the absolute value of 2x minus 5 is actually equal to a positive 2. That means I'm going to get two solutions again. So don't jump in right away and look at what the equation is equal to. Again, you can only make those conclusions when the perfect square group or the absolute value group is all alone on one side. Then whatever it is set equal to can determine how many solutions you have.